is this kind of thing I didn't hear last time. Okay, so today's class I will not introduce much, although I will try to introduce. हरजोत, क्या तुम्हारा क्या व्यू है इस सब्जेक्ट के बारे में? कैसा चल रहा है अभी तक?
सर अभी तक तो ठीक ही चल रहा है, जितने लेक्चर्स देखे हैं
अभी तक ठीक ही चल रहा है, ठीक है. So let us see how it goes.
तो बट लास्ट लेक्चर में जो वो बी मैट्रिक्स बताया थोड़ा सा
हाँ, वो थोड़ा ज्यादा हो गया.
तो
क्या हुआ उसमें?
सर उसमें 3x8 मैट्रिक्स बनता है ना, तो उसमें दिक्कत हुई है थोड़ी बहुत, और बस उतना ही बात है.
तो ये so numerical technique में you will always have to deal with these kind of things like matrix calculation कैसे हो रहा है, iteration कैसे हो रहा है, तो forward backward interpolation, forward interpolation, ये सारी चीजें ही है. This is what numerical technique is. जिसमें straight forward equation का solution नहीं होता है. So वो difficulty रहेगा, but if you so it needs more practice. और क्योंकि एंडसम एग्जाम जो है वो ऑफलाइन होगा, तो आप लोगों को थोड़ा और प्रैक्टिस करना पड़ेगा. सो यू गो इन ट्यूटोरियल, टेक सम प्रॉब्लम, एनी प्रॉब्लम, एंड जस्ट it's not a kind of calculation where you need to apply too much of an intelligence or conventional intelligence to find out something. The practice you have to do is just to use the matrix manipulation thing to get habituated with this. Although I will एक problem देखते हैं आज where there might be some thought process involved. Okay, so it will not be too heavy, but let us proceed with whatever we have. ठीक है. So you have, so basically what we do in FEM, let me just check if everything is okay. So it is being presented, it is being recorded, and you can see the screen also, right? Okay. So if sound is not good at any point of time, you have to tell just then. Otherwise, you will miss the part. Okay. So,
Okay, sir.
Okay. So so one of the techniques, there are many techniques, like there is finite difference method, and to solve any equation, when you can apply many different numerical approaches, and one of them is finite element analysis, which we are using. And you might have also seen something similar in fluid dynamics in the first part of this course. Okay. So what we basically do is you take any object, and then you divide it into smaller pieces. This is what we do. And we take one. So what are we doing exactly is that there are infinite amount of points in any object, whether or not it is small or big, it doesn't matter. I'm forgetting the name. There's this paradox, Baran-Tarski paradox. So a few of you watch Veritasium's video, no? No, but that is from Vsauce. That is another one. If you're not watching, you can start watching that also. Okay, so in one of the Vsauce videos, they explain about Baran-Tarski paradox. It says that out of a sphere, if you take all the odd numbers, so let us divide this sphere with the points which are, so you divide it into infinite number of points, and then you take all the odd points out, and then you take all the even points out, so you can make two spheres, no? So both of the two spheres will be complete, right? They will not be missing anything. But even then you will have enough number of points to make the original sphere as well. So it's like it's never ending process, and you're taking the sphere out of the sphere still that is there. Okay, so I am not going to explain this too much, but you can go and have a look if you are interested. So any object has infinite number of points in it, right? And when we divide that into, let us say, 10,000 points. So let us say I'm making small elements so that I have 10,000 nodes. So what am I doing exactly is that I'm discretizing this object. So I'm getting the information about this object by 10,000 points on this object, right? So I am never going to get the full information. And then it depends to what extent I want to have the information. Do I need to have all the information, or do I just need to have that much amount of information about the object from which I can do a good or handsome calculation to proceed with? It gives me an advantage because I don't want to make a full bridge or a full building, and I don't want to test it under an earthquake, whether it breaks or not. Rather, what I will do is I will take the material property of the frame which is going to be used in the building or in the bridge, and then I will simulate the situation of earthquake or tsunami or both combined, and then I will see if my simulation shows that the material will break or not. With a factor of safety, I can proceed to use that material for making the structure, or I can decide to go with another material or to look for a different material. So this is the motivation behind what we do and why we do. Okay, so now let us come back to a simpler situation and let us look at how we do it. So in the video lectures, which I will be sharing, you will be seeing the method of how we calculate the stresses and strain in a quadrilateral element. So today, let me discuss another kind of element, which is a triangular element. So this is called linear triangular element. Sometimes it is also called constant strain triangle, the CST element. Why it is linear? Because the safe function is linear. So the interpolation of the degree of freedom between node number 1, 2, and 3 is going to be linear. Okay. So the variation is going to be like that. And so from here we go to 0, and there it will go here 0, there 0. Okay. So at each node, the value of that safe function, so n1 at node number 1 will be having a value of 1. At node number 2 will be having a value of 0. Node number 3 will be having a value of 0. And the same thing. Okay. So the value of n1 will be 1, 0, 0 at node number 1, node number 2, and node number 3. And this will be true for other shape function as well. That is the property of shape function. Okay. And the classical way of deriving shape function is by taking a polynomial. So, so any degree of freedom, it can be displacement, it can be temperature, anything that can be described as a polynomial function. So let us say a0 plus a1x plus a2y and so on, or you can stop here. And using this information, you calculate the isoparametric relation between the nodal values of this degree of freedom and the continuous value. And from that, you take the inverse and all those things. And then that is how you find out the shape function. The other method, so that is the first principal method of finding shape function. The other method which we discussed was Lagrangian in the last video, I guess. And the third method, there is another method which is applicable in triangular elements, and that we will see very straightforward. We'll go there. So without spending too much time on the derivation, let us just know that the shape function for this element is described in this way. Okay. And when you break it in local coordinate system, so this becomes, I will call it epsilon, and this can be eta. Okay. And these are the shape function for the three nodes. So now we have the shape function. Now what are we going to do? How are we going to describe the displacement? So using isoparametric formulation or the information, we know that the displacement can be described as Ni di. Okay, or let me call it Q. So let me call the displacement, the continuous displacement, as Q, and that will be equal to Ni ui. Just hold on. Yeah, I'm in a class. Okay, so am I audible? Hello?
Yes, sir.
Okay. So, and you can see the screen, right?
Yes, sir.
Okay. So if I have to write the continuous field of displacement, I can write it like this, and I can also write the coordinate at any point of time. So xi is equal to ni. So x is equal to ni xi, and similarly y is equal to ni yi. Right. So this you are familiar with. Okay. Now let us describe. So if you have to describe the displacement in vectorial, in tensorial or in matrix formulation, then how would you do that? So u or v. So u is the displacement in x direction. So we are still dealing in 2 dimensions, and that's why we have triangle, not a tetrahedron. But in 3 dimension, things are not going to be that complicated. Whatever you're doing in 2 dimension, you just have to add on one more dimension. So in 2 dimension, you have two types of displacement. One is u1, which is in the x direction. So this is x direction, this is y direction. So displacement in x direction is u1, displacement in y direction is u2, or sometimes you can also denote this one as v and this one as u. Okay, and if it is 3 dimensional element, then you will have 3 degrees of freedom at each node. So you will have u1, u2, and there will be one in the plane of the screen, which will be u3. Okay, and this you have seen in Abacus when we were doing the lab course. You must have seen this Cartesian coordinate. So when you rotate the view, you will see this coordinate handle also rotating. Okay, so that visualization, if you want to see, you can go back to Abacus files and you can see that. So UV, if you have to describe, then you can write it as N1, N1, N2, N2, N3, N3 into U1, V1, U2, V2, U3, V3. Okay. So because you have 3 nodes, so node number 1, 2, and 3. So you have here U1, V1, you have U2, V2, you have U3 and V3. Okay. So you have 6 number of degrees of freedom there in this column vector, and then you have the shape function matrix, which is simply like this. And so if you want to calculate the total displacement at any point in x direction, so u will be simply this row versus that column. So n1 u1 plus 0 plus n2 u2 plus 0 plus n3 u3, and that's it. And similarly, v will only be multiplying because it only has finite value at these places. So it is going to give you the summation of ni vi, right? Because every other place, so all the odd numbers are 0, even numbers are having finite value of the state function. Okay, so this is how you get the displacement in terms of matrix. Now, if you have to calculate strain, how are we going to do that? Any idea? No idea?
No.
Okay. So just
No, means epsilon we will be half du by dx plus dv by dy होगा सर, बट अभी से और सिंप्लीफाई कैसे करेंगे उसमें.
okay, good. Okay. Okay. So what you said, who said it? Charvak.
Yes sir.
Okay. So you are right actually. So so epsilon matrix is actually del u by del x, del v by del y, then you have del u by del y plus del v by del x. So this much we know from our MM302 course. Okay, so we know from there in tensorial notation that the Green's strain can be written as del ui by del xj plus del uj by del xi. Right? So when it is normal direction, you only have this term, and when you have, so this is the normal strain, and this is the shear strain. Okay. So how are we going to do this in the form of matrix? So in order to do that, we will have to do a lot of different calculation. Okay. So I don't know why, just hold on. Okay. So what I was saying was that in order to do this using this information, so we have u so far. So we have this information, and from that we can see that we can calculate the strain matrix. And in order to do that, what we have to do is we have to do the partial derivation of the displacement matrix or displacement vector. So how are we going to do that? So let us say we want to find out del u by del x, and we also have to find out del v, but we also have to find out del u by del y for this one. Okay, so in order to find this one out, we have to do what? We will have to do del u by del epsilon into del epsilon by del x. And then for this one, we'll have to do del u by del eta and del eta by del x, right? So we will have to do first the partial derivation of in terms of the local coordinate system, and then we have to have a relationship between local coordinate system and the global coordinate system, right? So how can we can write this in this form. So we can write it as or if we have to write this, so instead of writing this, if I want to write this one, then I can write it as del x by del epsilon and del y by del epsilon, and del x by del eta, del y by del eta into del u by del x, del u by del y. Right? So I can write it in this way. Okay? Is
Yes,
it
sir.
okay?
Yes,
Yeah.
sir.
Okay. So the relation between the partial derivative with the global coordinate system and the partial derivative with the local coordinate system is known as, so this is that,
Jacobian matrix.
yes, so that is called Jacobian. Okay. And if you want to find out this one, then you simply have to invert this and then you will get the other relationship. Okay. So you can write this is equal to J inverse del u by del epsilon and del u by del eta, right? So this can be done easily. And J inverse can be defined as 1 by determinant of J and J22 minus J12 minus J21, J11. So what are these? These are the component of 2 cross 2 Jacobian matrix. So this is Jacobian matrix, right? So this one is J11, this one is J12, this one is J21, and this, okay? So instead of every time doing, you can use this formula to the inverse of the Jacobian matrix. So once we have, now we can come back to our original problem, which is strain in
So your
terms.
voice is breaking.
Okay, so are you getting my voice?
Yes, sir.
Okay. Okay. So the original problem was to define strain using this formulation. And we saw that we will have to do the partial derivation with respect to the global coordinate system. And all this calculation is going on element wise. So in each element, we are doing this. So we know that each element we have designed in our local universe with our local coordinate system. So we need a relationship and we got it from the Jacobian matrix. Okay. So now if we have to change it in terms of, so now let us say that if I have to find out del u by del x, del v by del y, and del v by del x plus del u by del y.
So your screen is not visible.
Oh, but it is being shared. It's not, is it not visible?
No, sir.
No, sir.
No. To avoid an infinity mirror, don't share your entire screen. Well, okay, so I'll stop sharing and then I'll share again. Okay. So is it visible now?
No, sir.
Hmm?
No, sir.
No, sir. क्या हो रहा है भाई? Why thing is not visible? So I join this. I can see the screen. Why you
Yes,
can't
sir.
see?
Now it's visible.
Okay, fine. Okay, so I was saying that I have to find out this strain matrix, and in order to do that, let us do something, and then we will see how are we getting that or not. Okay. So in order to do that, I am going to take this J inverse. So J inverse is this. Okay, this one. I'm going to use that. So what by determinant of J is going to be out, and then I will have J22 minus J12, and then have 0 and 0 and 0 and 0, and minus J21, J11, and then minus J21, J11, J22, J1. Okay. And then I will have this term. So I will have del U by del epsilon, del U by del eta, del V by del epsilon, and del V by del eta. Sorry, eta. Okay. So if this is not making sense, you multiply this row with this column. So what will you get? You will get only the first two terms, right? So the first two
Yes.
terms are J22 into del U by del epsilon. So that will be simply this. So that will be simply this. Okay, because J inverse is this, right? So if you multiply this with that, what do you get? You get J22 del U by del epsilon, right? And then you get minus J12 into del U by del epsilon. And this is what you are getting here also when you multiply this with this, and then you get nothing and the other two elements, right? Because those values are 0. So the first row into column will give you del U by del x. The second row into column will give you del V by del y. Okay, because for del V by del y, you will have to do similar kind of thing. So you will have again J inverse, and then you will have, so minus J21 into del V by del epsilon, J11 into del V by del eta. Okay. And then the last term, you have no element which is 0, right? So here you will get, why you are getting non-zero elements? Because you are actually calculating del U by del y plus del V by del x. So is this clear or not? Hello?
Yes, sir.
See, if it looks a little difficult, so let us look at
So
J
in
inverse.
video, you just said that determinant of J is 1/6 of volume of element, but you didn't show it that time.
Yeah,
So,
that is the assignment which I'm going to give you.
okay, sir.
So in this case, the determinant of J is going to be double of the area of the triangle.
Okay, sir.
Okay, and that is what you need to prove. So there a little bit of thought process will be required. And especially I would like you to prove that using geometry rather than analytical mathematics. You can try using geometry, and if that doesn't work, then you can come back to the formula for an area of an of a triangle and all those things. Okay. So where were we? We were here. So Jacobian, how do you calculate Jacobian? So J, let us say J11. J11 is del x by del epsilon. Do you know, or can you imagine how you're going to calculate this? If not, then I will just explain one component of J matrix, which is J11, which is del x by del epsilon. How are you going to calculate this? Then what is x? X is Ni xi, right? So you have coordinates of the 3 points. So our 3 nodes, you have x1 value. So similar to the displacement values, you will also have coordinates x1, y1, x2, y2, and x3, y3. Okay. And you have your node shape functions. So n1 x1 plus n2 x2 plus n3 x3. So this will become epsilon and whatever is the value of coordinate. It will be some number, right? And then eta x2, and you will have 1 minus epsilon minus eta x3. So this is your x, which is equal to x1 epsilon plus x2 eta plus x3 minus x3 eta minus x3, sorry, epsilon x3 eta. This is your x. And then you find out the value of del x by del epsilon. So that becomes x1 plus 0 plus 0 minus x3 minus 0. So it simply is x1 minus x3. So now can you imagine what are we doing? Or how you're going to do it? Okay, so if you have to calculate a strain, the stepwise process would be to first find out the shape function. Okay. The second process is, if you have to find out the strain, then the second process is to find out the Jacobian matrix. So in order to find out the elements of Jacobian matrix, which is these 4 expressions. So for that, you need to find out x as Ni xi and y's at Ni yi, right? So when you do del x by del epsilon, you get the first term, which is J11. Then you do del y by del epsilon, and then you get what? You get J12. Then you do del x by del eta, and you get J21, and similarly J22. So we have the expression of x. So we can find out del x by del epsilon. We can also find out del x by del eta, which will be, so 0 there, x2, 0 there, 0 there, minus x3, right? So this is my J11 and this is my J21. Similarly, you can find out J22 and J12. And then once you have all those 4 things, you can put it here in this matrix. And using this, you can calculate the strain. Determinant, of course, once you have 1, 2, and the other 2 elements here, then you can find out the determinant, right? So that is not a difficult job to do. Okay. So now we are here and we have to find out. So where are we? Okay, so we have to find out strain. No? Where is it? Here. So we have reached here and we still have to deal with this one, this matrix, del u by del epsilon. So let us proceed from here. So epsilon, oh sorry, not epsilon, the strain can be written as J22, J12, 0, 0, 0, 0, minus J12, J11, J22, J12, J21, J11 into del u by del epsilon, and then del u by del eta, and then del u by del, del v by del epsilon, and del v by del eta. So now we have to deal with this. So let us call this A matrix, this one. Oh, I also have determinant of J. So let us call this determinant of J plus this thing as A, okay? And then I have this matrix, which we are going to deal with. So what is this? This is simply the partial derivation of the displacement field with respect to the local coordinate system. How are we going to deal with this? So if I have to find out del u by del epsilon, how am I going to define u? U is defined as ni ui, right? So del u by del epsilon will be defined as del n by del epsilon into the nodal values of displacement field. Okay, is this clear?
Yes, sir.
Okay, so here what are we going to do is we are going to make a matrix which will be del n. So we have three shape functions, so it is going to be repeated 3 times. If we are dealing with linear quadrilateral element, then we will have 4 repetitions, and those repetitions are going to be del n1, del epsilon, and then del n1 del eta, and then del n1 del epsilon, and del n1 del eta, and 0, 0, 0, 0. And the same thing is going to be repeated for shape function 2 and shape function 3, because we have 3 nodes. So here it will be del n2 and all the same story, and 0, 0 there, and 0, 0 there. And here it will be del n3 and the same story, 0, 0 here, 0, 0 there. Why it looks in this way? Because at the end you have to keep this, which is u1 v1, u2 v2, u3 3. Okay, so if you multiply this, so how many are there? 6, no? So 6. So this is 6 cross 4. So we have rows into columns. So we have 4 cross 6. And this is 6 cross 1. Right? So you will get 4 cross 1. And then you have 3 cross 4 here. This one, A matrix. A matrix is 3 cross 4. Okay? So if you multiply this with this, what do you get? You get del n1 del epsilon into u1, nothing for v1, and then nothing for v2, nothing for v3. So you only are multiplying with the x direction. So del n1 by del epsilon into u1, del n2 by del epsilon into u2, del n3 by del epsilon into u3. Right? Are you getting it?
Yes, sir.
Okay. So this matrix is broken into pieces. So one is taking the partial derivative with respect to partial derivative of the shape function with respect to the local coordinate system, and this you have from the beginning. Okay, so now I can write it as A is a 3 cross 4 matrix, and then this is 4 cross 6 matrix, which is, let us say, G, 4 cross 6, and then you have the displacement vector, which, so D is 6 cross 1. Okay. So at the end, what will be the size of the matrix you will get? What will you get at the end when you do this?
Sir, 3 cross 1.
What?
3 cross 1, sir.
Yeah.
3 cross.
So this will be 4 cross 1. So 3 cross 4 into 4 cross 1 will be 3 cross 1. do we have 3 cross 1? What do we have? Strain. What is strain? Which is 3 cross 1. So are we happy? So this together is called B matrix. A and G together, right? So this one multiplied with this one is called B matrix. And then in a very short notation, strain is written as B matrix. And this B matrix will be coming when you do the calculation for stiffness of the element. Okay. So this is what we have established. And in very short notation, if we write all the steps, then first step is X and U. X is equal to Ni Xi and U is equal to Ni Ui. This is coming from isoparametric formulation. Then second step is finding the Jacobian, okay, and the inverse of it. The third point is to arrive at strain is equal to B matrix into D. And then fourth is you have to calculate the stress. The stress is equal to D matrix into strain, right? So D is what we usually call when we are not writing finite element notation, then we simply write it like this, right? So this is elastic modulus in the scalar form, right? But here it is not in the scalar form. Here it is in the matrix form. So we don't call it E because E is elastic modulus, which is one material property. Okay, so you remember that the elastic stress strain relationships are not given by elastic modulus. No, if you remember our initial chapters in MM302, you would realize that the elasticity is different for a crystal in different direction. Okay, so if I have so what is this? Okay, so if I have a crystal structure which is like this, which is like a hexagonal closed pack. Okay, and so I have a C axis and then I have A axis. So this is A, this is A, both of them are same. So anyone could be A1 or A2. And then I have a C axis. So you know that in HCP crystals, the third axis is not equal to the other two axes, right? And I've drawn it tilted, but because it's HCP, it will be orthogonal in all the direction, the angles. So you know that this atom and this atom is at a higher distance in comparison to this atom and this atom, right? So atom number 1 and atom number 2 and atom number 3. So the distance between atom number 1 and 2 is smaller than the distance between atom number 1 and 3, right? So they are going to behave differently in that direction. So if you find out a plane which lies on this, so which is parallel to this plane, you will have more number of atoms in comparison to a plane which is in this direction, right? Because you are having atoms at a longer distance on this one in comparison to this one, right? So now imagine playing billiards in these two planes. So if you are playing on this plane, if you're playing snooker on this one, then if you hit one ball, that energy will be transferred to the surrounding balls very easily in shorter period of time. So more balls will be getting the momentum. The momentum will be transferred to large number of balls, right? Because the energy dissipation in traveling from here to there will be less. But if you are playing the same game on this plane, then you will have to hit it harder in order to hit the same number of balls on that plane. Is it making any sense, or it was a bad analogy? Are you guys there?
Yes, sir.
Okay. Okay. So the point I wanted to make was that elastic modulus in different direction is different, and that is what we have learned from stiffness tensor, which was a fourth rank tensor. If you remember S1111, S1112, and so on. And the inverse of that was compliance tensor, which was C1111, and so on. And those are not equal in all direction. And we apply strain incompatibility and isotropic behavior of the material to arrive at three independent variables or two independent variables for an isometric cubic crystal, and those two independent variables are E and mu. Okay, so E and mu independently are none of these. A combination of this uh, becomes a component of that tensor. Okay, and that we have studied in great detail. So we will have that. So if it is isotropic material, you have to use that kind of matrix. If it is plane stress condition, you have to use a different matrix, a different D matrix, and that will be defining the relation between the stresses and the strain. And the other difference between what we learned in our mechanical course was that we used to write the stress in this form, right? So we used to write it in 3 cross 3 is equal to a stiffness tensor, which was 9 cross 9. So 81 component, and a strain tensor 3 cross 3. So this is what we used to do in our mechanical behavior. So continuum mechanics. But in finite element analysis, we make it easier. So we make the stress as column vector. So we have sigma 1, 1, sigma 2, 2, sigma 3, 3. And then we have sigma 2, 1, and sigma 1, 2, and sigma 1, 3. So instead of having 9, we have 6, and then we have symmetry. So sigma, sorry, 2, 3. So we know that sigma 2, 1 is equal to sigma 1, 2. So we are not going to waste our time in writing that component or making even 3 cross 3 with 0 elements. It's better. Why are we doing this? Because all of this is saving space, saving RAM of your machine. Okay, so if you write the stress tensor in this form in comparison to if you write a stress tensor which is like sigma 1, 1, and we know that sigma 2, 1, so 1, 2 is equal to sigma 2, 1, what are you going to do? So you are going to save maybe in the form of sparse matrix that you don't want this information because this information is redundant. This is equal to that, right? So sigma 2, 2, and then you have sigma 1, 3, which is equal to sigma 3, 1, and then you have sigma 3, 2, which is equal to sigma 2, 3. So this is redundant, this is redundant, this is redundant. So in order to save space, it is better to write in this form. Okay. So here we write it in this form. And then if you have plane stress, then this will be going out, this will be going out, this will be going out. So you'll have only 3 there. Okay. So the D matrix is going to be different, and strain is also going to be compressed. In place of 9, you're going to have only 3 components. So we are going to have sigma xx, sigma yy, and sigma xy because it is 2-dimension, right? So we are not in z direction. So third is anyways gone. So now if you have to write the relation between the stress and strain, the D matrix for plane strain condition, if you remember, you will have Lamy is constant. So that will look like this into 1 minus mu, mu, 1 minus mu. So we have 1 minus 2 mu divided by 2, and rest of them are 0 into strain. So epsilon xx, epsilon yy, and gamma xy. Okay. So this is for plane strain. And for plane stress, the only variation going to be is 1 minus, so D matrix will change to 1 minus mu square 1 mu mu 1 0 0 1 minus 2 mu and 0 0, and this will remain same. Okay, so this is my D matrix, and also this one. This is for plane stress and this is for plane strain. Okay, is this clear? This is the same thing. You go to the book of Dieter and go to the initial chapter where they define the relation between elastic stress and strain. So there you will find that this we have already discussed. Okay. So there we discussed a different formulation, which was epsilon ij is equal to sigma ij divided by E minus, so no, 1 minus mu by E minus mu into sigma ij delta kk, right? So we used it in this tensorial form, which will appear, if you write it in matrix form, it will appear in the same way. Okay, so here we are describing the relation between stress and strain, and this is the other way around. Okay, so if you write it so if you write the relation between sigma ij with, so sigma ij is equal to some function of epsilon ij, then you will have this Lami's constant also appearing. Okay, so you can revisit that and see that we have discussed this before. Okay, so coming back to our discussion, which was this. So now we have arrived here. We can calculate from displacement, we can calculate Jacobian, we can calculate the strain, and then we can calculate the stress. Once we have the stress and strain with us, and actually we don't need stress, we can also calculate the stiffness matrix of an element, and there we will have to do the integration. Okay, so which we will do in the form of numerical integration, and that we will not discuss today. And so the simple way of doing that is B transpose dB, and then you will have d epsilon d eta, and then you also have the thickness of the element if it is in plane strain condition. Okay, if it is third dimension, then you will have another local coordinate there. So epsilon zeta, and then I don't know, something psi. And then you will have triple integration here. Why -1 to +1? Because we know that local coordinate always goes from +1 to -1. Okay. So this is, if epsilon value is +1 here, -1 here, 0 here, and eta value, no, this is eta. Eta +1 here, -1 there, and epsilon is +1 here, -1 there, 0 there. So the integration over the element always goes from -1 to +1, and this we will do in the form of numerical integration. And so we will end here, and in the next lecture, maybe there will be explanation on how to do the numerical integration. Did you understand anything or nothing?
Yes, sir.
Okay. So in the tutorial, you take the example. So what example you want to take? You want to take a triangle, simple triangle. Okay, the assignment which I wanted to give was, but that I couldn't discuss. Okay, so let us take 2 minutes here. So the safe function in constant strain triangle can also be represented as N1 is equal to the area divided by some area A1, which I will tell you what it is, and the total area of the triangle, this triangle. N2 will be simply A2 by A, and N3 will be simply A3 by A. And what is A1, A2, A3? A1, A2, A3 are defined by a point, any point, anywhere. It can be anywhere. Okay, it can be anywhere in the triangle. So let us take a point here, which is, let us say XY, and you have coordinate system X1, Y1, X2, Y2, X3, Y3. So, and this is node number 1, this is node number 2, this is node number 3. Okay, so with this point, you can you can divide the whole triangle into 3 different areas, right? So in front of point number 1, whatever triangle is forming, the area of that triangle is A1. Okay. And now you know. So this is A2 and this is A3. And the same function N1 is A1 divided by the whole area of the whole triangle. And N2 is equal to that. N3 is equal to that. Your assignment is to prove this. To prove what? To prove that, and also that the so let us take a matrix which is x1, so 1 x1 y1, 1 x2 y2, and 1 x3 y3. And the determinant of this matrix, so if it is A, then determinant of A is 2 times the area of the triangle. So this is what you have to prove. This is a very simple task. Okay. So this is what you have to prove, and try to prove it geometrically, not, just multiplying, finding the determinant. Don't do that. Try to do it geometrically. So of course, for determinant, you have to calculate what the determinant value is in terms of mathematical formulation. But how that is telling you the area of the triangle. Do you understand the question?
Yes, sir.
Okay. So try doing this, and we end this session here. Okay. So I'm closing the call now because it is already late.
Yes, sir.
Okay.